All right, thank you for joining us today. This is our webinar on Geotechnical Radar Data Integration. It is an interactive webinar in the way that you will be able to ask questions live to our wonderful panel who's here today that are experts in this topic. We'll run until 9 a.m., so 1 hour to field your questions, and we hope you'll engage with our panel today, who I'll introduce in just a moment. This webinar is brought to you by the Geotechnical Center of Excellence at the University of Arizona. We are industry funded and member led, and we are an interdisciplinary center working across academia and industry on collaborative geotechnical research and education with the goal of bridging gaps within and between academia, industry, and fields of study. If you're interested in learning more about the GCE or membership with the GCE, please send us an email at the address you see there, gce@arizona.edu. And this webinar aligns with one of our professional development courses on the topic of geotechnical radar monitoring. If you're interested in this course, you can still register for the course. It will be available until 2025. It is online and on demand, and it covers the topics ranging from satellite-based SAR and SAR to ground-based SAR and RAR, as well as talking about the capabilities, limitations, how to interpret radar data, and real-world examples and case studies of the use of radar data in mining applications. And then I want to take a moment to thank the GCE member companies. With their support, we are able to develop courses such as the Geotechnical Radar Monitoring course and do other applied research and outreach that the GCE does. So thank you very much to all of our supporting companies for making this webinar possible and all of the other work that the GCE does. And now to introduce the GCE webinar team that's with me today. So I'm your moderator. I'm Jillian Noonan. I am a senior R&D engineer with the GCE. And along with me are Julia Potter, who is the director of the GCE. Thanks for joining today, Julia.
Thanks, Jill. Hello, everybody. Thanks for being here today.
And Allison Brucey, who is the GCE's program coordinator. Hello, Allison.
Hi, Jillian. Thank you, everybody, for joining us.
And now it's my pleasure to introduce to you our expert panel who will be answering your questions today. We have Derek Rubish, who is Senior Geotechnical Engineer with BGC Engineering. Derek, thanks for being here and for giving us your time today.
Yeah, happy to be here. Thanks.
Also joining is Charla Kotsi, who is Group Geotechnical Engineer with Roytech Mining out of South Africa. Hello, Charla.
Hi, everyone. Thank you so much for having me today.
Also joining us from Ground Probe is Albert Cabrejo, who is the Global Practice Lead for Geotechnical Advisory. Hello, Albert. Always good to see you.
Hello, everybody. Pleased to be here. Thank you.
Cliff Preston is joining us from IDS GeoRadar. Cliff is the Director of Mine Monitoring. Cliff, thanks for joining us.
Hi, everyone. Thanks for giving us the opportunity today.
And Paolo Farina is on our panel today. Paolo is the Managing Director for GeoApp. Paolo, we're always glad to have you on a panel.
Hi, everyone. Thank you very much for giving me this opportunity.
And we have Will Conrad. Will works with Canary Systems and is a monitoring technology solution architect. Will, great to have you today.
Thanks, everybody.
And we have Chad Williams. Chad is an advisor to the GCE, as well as working at Rio Tinto as a principal geotechnical engineer. Chad, thanks so much for being here.
Yeah, thanks for having me.
All right, thank you so much to our panel for devoting their time to us today and to our participants. And now I'm going to run through for the webinar attendees how to participate in this webinar in an interactive way. So first of all, you are muted and your video is off. So in order to ask a question, you will do so through the Q&A. You can find a button on your Zoom control panel that says Q&A. Looks like the button here on the screen. So you click that button and it will open up a window where you can type in a question, and you can do a thumbs up for questions that others type that you like. If questions are rated higher, we'll pull those ones first. You can enter your questions anonymously. And at the end, this will be a recorded webinar that will be posted both to the radar monitoring course and also to the GCE's YouTube page. All right, so we have some questions lined up. We had a survey that we sent out prompting for pre-submitted questions, both from the general public and from our radar course monitoring participants. So we're going to run through those, but at this time, I will welcome anyone in live attendance to begin entering any questions in the Q&A. Allison and Julia will be fielding those questions, sorting through them, and then I'll be putting those up on the screen in a similar manner to address. So at this time, I welcome you to enter any questions that you'd like to ask of our panel on the subject of geotechnical radar integration, data integration. So we'll start with this question here that came in through our survey. And I'll read each question and then I will open up for the panel to discuss. So this question came in and asks the panel, could you discuss how to make processed data compatible, such as deformation data in millimeters from ground-based radar and satellite INSAR, considering that ground-based radar has pixel resolution or sizes, while INSAR manages resolution based on bandwidth? How do you make both data sets comparable? So for this question, I will ask Paolo Farina to please start with, and then we can open up to the rest of the panel for additional comments.
Yeah, thanks, Jill. So that's a very good question, because sometimes now we push slope monitoring practitioner to integrate data, but it's important to first, before starting to integrate data, to be sure that we can make the different dataset comparable. And when it comes to integrating radar and INSAR, the first things to consider is, in my opinion, the different line of sight. Okay, because INSAR has two different line of sight, ascending and descending, with a significant vertical component and a lower horizontal component, mainly along the east-west direction. So when you have the opportunity to combine ascending and descending data, you can decompose the vector into the vertical and east-west components. While when you are looking at radar data, typically you have only one line of sight, okay? And in most of the cases, the line of sight has a significant horizontal component, while the vertical component typically, depending on the, of course, on the installation setup, is lower. So it's important to understand that we have these differences. So that's the first point. So considering that if you compare the magnitude of the two line of sight, you may have significant differences. The other important element is the pixel size. Both INSAR and radar are based on pixel. And if you use high resolution INSAR data like TerraSAR-X, you may have a pixel of 3 meter by 3 meter, or even 1 meter by 1 meter. And in this case, the difference in resolution between radar and INSAR is not that high. Okay, so you can compare a bunch of radar pixel with a few INSAR pixel. Okay, that's what you can do. Another important element is the scale of displacement that we typically expect to address with the radar and with INSAR. What does it mean, the scale? INSAR is very well known for the capability of measuring very slow movements over long time, so millimeter per year, let's say, millimeter per month, while typically radar, in the majority of the cases, is used to measure faster movements, let's say millimeter per day, millimeter per hour, millimeter per week or per month, when you have good data with good post-processing, okay? So sometimes it may happen that you compare INSAR in areas where you have with radar in areas where you have just a few millimeters per year of movements. And of course, the risk is that you are comparing some displacement signal detected by INSAR with noise detected by radar because of this difference. Of course, there are all better processing for radar to, let's say, also make radar capable of measuring slow movements, but in the majority of the cases, this is the difference. And also INSAR is not capable of measuring fast movement. So you may have lack of data in the fast moving sector of the pit where you have good radar data, okay? So that's something to be considered. In my experience, it's important to integrate those data. Any GIS software can do this. I mean, you can import the radar pixel point clouds as well as the INSAR data as shapefile, and then you can compare the two. And once you understand the different line of sight, you can even compare the correct, let's say, the displacement and also compare the time series. Or you can even use available platform that can do already this. There are a few on the market, but this is something, functionalities that are coming more common and common every day.
Yeah, I have a couple of comments as well. So first of all, I agree 100% with Paolo on each one of the points that he made. Maybe something to add to the answer is I've seen sometimes that you get different magnitudes of displacement, but by large orders of magnitude between INSAR and ground-based. So sometimes that is related to the loss of coherence or existence of high coherence to the point of not rejecting pixels. So sometimes you get maps in the ground-based radars with lots of pixels and the whole surface covered with pixels and information, while with the INSAR you don't get some pixels or some areas. That's sometimes it is caused by the lack of coherence and the filters that are applied to the INSAR data. So as Paolo was saying, INSAR is mostly used for slow movement. The rapid movement is as fast as it can happen within the frequency of revisiting time, so 4 days or 11 days. So if things move too fast for INSAR, it may lose track of the formation. That tends to happen less with radars on the ground, or have a more frequent revisiting time to avoid that and at a larger extent. There are other times that I've seen a couple of cases where INSAR, despite the rapid movement, INSAR retained the high coherence, which means the pixels were not filtered out of the data set because of coherence, but still they went beyond the ambiguity threshold for the INSAR. It could be 3 millimeters, 5 millimeters, 6 centimeters. So sometimes you get those differences in magnitude in which the INSAR detects something very slow that you know it is moving in a coherent manner with other instrumentation in ground. So it is important to have that clear, and redundancy of instrumentation sometimes help to address those doubts.
All right, thank you, Albert. Will or Chad, would either of you like to speak to the use of these dual types of monitoring within a integration platform or within an operational site? Will, I see you've unmuted.
Sure. So yeah, definitely possible there as far as from the integration platform sake. Definitely the different, different frequencies do play a part in it all. So being able to grind that data together and show that data combined with the different displacements and comparisons and so forth, there's definitely possible and definitely manageable there as far as making sure that the information is shown and available for that type of analysis.
I think, yeah, when we use INSAR, we're normally looking at very large hazards, very slow movement over extended areas. And so the resolution isn't usually a critical thing. We're not usually looking at very small movement areas with INSAR. So when we integrate it, usually that difference it doesn't really matter to the geotechnical analysis. There's lots of GIS software that can do it. We use Leapfrog mainly because all of our geology is managed through Leapfrog. So we just bring it in as a CSV and plot the points on the surface and compare it to the structure and geology that way. So usually we go through about once a month, once we get an INSAR report, and then do a detailed comparison to our ground-based monitoring systems in the geology.
All right, thank you. Any other comments from the panel on this question? I think we've answered it quite well.
I think that ultimately what we are looking is for trends on any instrumentation, more than looking at the exact number that a prism or a radar or INSAR may give you. What you are looking is for trends from the risk management point of view. From the point of view of analysis and calibration or perhaps models, then the exact number may be important to have. But that's for modeling. It probably gives you more time. But if it is for safety matters, you are looking for just the trends.
And I think there's a question that came in the Q&A. I don't see it in the slide yet, but we'll pull that up in just a minute. Let me pull up one. Oh, there it is. Let me pull that up. So with regards to the use of INSAR and ground-based radar or other ground validation systems monitoring movement, how could measurements obtained by an INSAR system be calibrated based on ground validation systems to generate an early warning system for remote areas where direct measurements of ground deformations are not available?
I can take this one.
Yeah, go ahead, Paulo.
Yeah, I would never talk about early warning system using INSAR, okay? Because early warning system brings the idea that we have something in near real time, and we know very well that INSAR, even in the best case, can be, let's say, updated over a weekly base or let's say bi-weekly base. So, but on the other hand, I'm really convinced that INSAR should be used as a way to identify in the early days anomalous areas where anomalous behavior are occurring in time and in space. That's why I always recommend to process INSAR data, to post-process INSAR data with the scope of identifying where progressive trends are ongoing, of course, at the scale of velocity and acceleration that INSAR can cover, and also to calculate from INSAR data the strain parameters, because strain is another important parameter that we have always to consider, because where we have accumulation of angular distortion or horizontal strain, it's where we may have development of cracks, trench, and instabilities, not the boundary of instability. So that's why if you receive as a mine site INSAR data, in my opinion, it is fundamental to implement all over the INSAR points a post-processing capable of identifying hotspots where those two, let's say, elements, let's say temporal evolution and spatial evolution, spatial pattern, are developing. And this could be used as a sort of, if we want, early warning system to activate more action in the field. So, for example, activating field inspection or checking drone images in remote areas or checking other data on the ground. We may have prism, GPS, piezometer, inclinometer. That's something that I always recommend to my clients to take advantage of INSAR in this way.
Very good. Thanks, Paulo. Any other comments, Albert?
I think that in ground probe, we always recommend the INSAR technology as the point of entry to a complete approach of monitoring with other instrumentation. Maybe not just at a pit level, but an overall mine property or mine concession level. Because with INSAR, you can get information about the formations and processes that are happening all around in large areas. So it is a very, very smart way to get information and assign money, resources to specific points of concern that may have been revealed by INSAR. So it gives you a very good way to manage the budget that you have for your monitoring. And Alejandra, you are talking about places where measurements on the ground informations are not available. So I know sometimes there are parts of the planet where it is difficult to deploy an instrumentation around. They may be hit, stolen, vandalized. So INSAR could give you that information with no touch on the ground. And maybe if you find points that are critical, maybe in-ground instrumentation that's difficult to steal and not attractive, may give you a possibility to do some additional critical monitoring, live in-place inclinometers, for example, in an area that you know the formation is happening from the INSAR. There is a very well-placed inclinometer with piezometer, perhaps. And Zipsabodne is very much a fan of the extensometers, live extensometers. They don't tend to be anything like fancy, not too stealable, if you like. So that could be another good system for live monitoring of those areas that where it's difficult to get measurements on the ground because of vandalism. Apart from that, it would be interesting to understand the particular situation about where you cannot install instrumentation on those areas, and then have a discussion about it.
Thanks, Albert. And I see we have one new panelist join us, so I'm just going to introduce very quickly Priyanka Narshai, who is a geomatics engineer with Geotech Mining, has joined us. Priyanka, thanks for joining us. No worries about being late. We're just glad you're here.
Thank you so much. Happy to be here.
All right, any other comments on this question? We have another live question that I'm going to pull up next. All right, so this question is from Alexi with regards to 3D vector generation from radar data. Alexi specifically asking about 2 ground-based radars and 1 satellite radar, but I'll also maybe open this up to discussions on just multiple ground-based radars, as I believe, Cliff, you have a presentation on vector analysis using radar data in the radar course. Chad as well, I know you have some experience with vector development using multiple monitoring tools. So would either of you like to perhaps start off with this question? Cliff, I see you've unmuted.
Sure, yeah. Yeah, I mean, I guess definitely it's theoretical possible, but you have to consider the things we talked about before with INSAR. You know, you have often different size pixels, a lot different density of the pixels as well, and locations, and then also, you know, different max velocities or measurements that they can take in measurement windows. So it's really important just to consider all that when you're using it. I think most people probably just use, in this case, INSAR data and the line of sight to, like, you know, just qualitatively understand directions, because you probably have a good idea of what direction it's going already based on just gravity and where it is in the mine and the geometries. So, you know, it can be used to confirm that mostly. I guess you can pull it into some of their software to actually calculate the vectors if you want. And yeah, I mean, it could be interesting for sure. I know there's some papers where people have done some type of things like that. Yeah.
Chad, do you have anything to add?
I think it's mathematically possible. I think it'd be better if you had 2 satellite radars to define basically in a plane a 2D vector. It'd be easier to combine 2 2D vectors, but it's really hard. I mean, we tried to do it with the mainframe, but like Cliff was saying, the data sets are so different, and they have some limitations. It's very hard to actually get a vector actually having magnitude and direction. It's maybe easier just to get a trend, to estimate a trend. And we were able to do that with MainFay, but we're never super confident in it, so we didn't publish it. But yeah, it's very difficult. It also depends on like what part of the pit you're monitoring. And so if it's, if it's a south wall or something where you don't get a great vector from INSAR, or the movement's maybe not in that 2D plane, it could be very difficult. So it really depends on the aspect of the pit and the direction of movement that you're trying to calculate, and the location of the two radars too. I would say it'd be very difficult to get something reliable, but general trend might be possible.
I can add something. In my experience, I never tried because I have some doubts that from a practical point of view, it's easy to do it. I mean, to get reliable result. What I did in several cases is to integrate, let's say, vertical and east-west movements from INSAR with north-south movements from GPS or PRISM. Because this is, let's say, the scale of movements that you get for those technologies is very similar. And so it is more likely, to my understanding or experience, to get reliable result, to understand, to create a vector where you have, let's say, a few GPS showing also the north-south, while you have a lot of INSAR points showing the east-west and vertical. So in this way, making some assumption, of course, you can try to understand the orientation of the displacement vector for a large area, not just here and there. That's what we try to do in several cases.
I mean, GPS units are so cheap now, and they'll give you a nice 3D vector over time.
Exactly.
Prism's been around for 20 years or 30 years, and they're great. So I mean, if you're a site engineer, I would put effort into that to get a 3D vector with a method that's reliable.
I think that's usually one thing that we would recommend in a lot of those cases, like go put a GPS there because it's a lot higher accuracy and 3D anyways. If you can access it. Yeah.
I agree. I think that there are cheaper, more reliable ways to get 3D vectors. There are GPSs, there are prisms. That's probably much easier. If you don't have access because of the instability, you don't have access to install them on the ground. You could install them perhaps with a drone. That's not something too crazy to think about at the moment. Nowadays, I mean. And keep in mind, when trying to compare INSAR versus ground-based data, INSAR tends to be more of an absolute magnitude of displacement because the area that it scans is so vast that it for sure will find some stable points around to use for atmospheric correction. The ground-based radars, they are inside the pit, sometimes even moving with the slope where it is deployed, with stable reference areas or persistence carriers on slopes in front of them that are moving as well. So basically, ground-based radars are always measuring differential movement between what is the most stable versus the most unstable. So if you are trying to get vectors of movement, yes, mathematically it's possible, but I think it would only become reliable at later stages of the displacement when the magnitude of the noise of the technique that you are applying, including atmospheric correction and movements of the device you are using, when that noise is much smaller, 10 times smaller than the real magnitude of the movement you are trying to measure, then it may start to make some sense to apply the technique. For smaller movements, let's say preliminary information, which is typically what you try to get with INSAR, very early warning, where the movements are very slow, 1 millimeter per year, as Paolo said before, 1 millimeter of movement per year is easy. The same amount of noise that a ground-based radar would give you on a scan-by-scan basis on a complex environment. So it's difficult and may only make sense at large amounts of movement already, which makes me wonder if it is still interesting to to get to know the vector of movement, or if you are already in critical situation and you should be thinking about the evacuations and more operational plans. But no, for sure, the vector is always important to know.
So it can be done, but maybe not a practical everyday monitoring technique. So this question came in live, which is very similar. And I think we can confirm that we've discussed that prisms and GPS are the best tools for getting vectors, doing vector analysis in slopes, and that radars are a complementary tool that measure a line of sight displacement, but can be used to develop vectors, but maybe not as practical as just installing some point measurements at those locations. Can we confirm?
I agree.
All right, so we're about halfway through the webinar. So I see there are some questions coming in the Q&A. Thank you for those who are submitting questions. I'm going to go back to one of our pre-submitted questions here, and I'm going to ask Will to comment on this first from our panel. So Will works with Canary Systems directly with some integration platforms that are offered at Canary. As Paulo mentioned, there's many different offerings for different integration platforms. So Will can speak to Canary, but there are many options out there, just noting that. But just general tips, Will, on how to make integration data between surface radar data and subsurface monitoring tools work more properly or efficiently.
Sure. So I guess the main tip for proper efficiently is to make sure you do have that some sort of integration platform in place. It's especially with the amount of data being captured on sites these days, spreadsheets get overwhelming. Generic databases without a front end getting overwhelming as well pretty quickly. So that would be the main tip, just to have something in place already. And then really overall, working with the different radar vendors and so forth, there's usually multiple ways to get data from system to system. So CSVs can be an option. So maybe be with the radar data, it could be a point cloud type of CSV. So you have a northing, easting, and elevation component with displacement or any sort of other metadata associated with those readings that can be brought together with the integration platform. There's also what's called APIs, so application programming interfaces, which are pretty much calls to databases with a response back. That can gather that data in itself. So there can be automation components associated with that between different platforms that are set up between the radar integration platform to make that data integration component really seamless, so without having to have much user input. With the integration of the subsurface data, there's tools available that can bring that data into a 3D kind of interface within the actual software itself, and being able to bring that point cloud in from the surface radar, combine that with, say, an inclinometer. So with inclinometers, you could maybe have a cumulative deviation kind of component that you found some sort of vector for with that movement direction for the entire hole. You can combine with the radar displacement direction that you can gathered, as well as you sort of maybe compare that with your downhole piezometer readings with elevations or pore pressures, and have the area-wide kind of boundaries for any sort of areas that you're concerned with for any sort of movements, and be able to save those and pretty much alarm off of those as well, depending on, of course, the limitations of the radar and taking that into consideration, as well as some of the limitations of those other sensor types as well.
Paulo, I see you unmuted. Do you have something to add?
Yeah, something I typically recommend to do is to draw cross sections and to show on the cross section the vectors that you may have from surface displacement data, like from GPS Prism or from INSAR. Wherever you have Vertica and these 2S, you can combine the two components to get the magnitude and the angle of the vector. Or even simply with the line of sight of radar, drawing the line of sight of the radar of each point and the magnitude, and try to compare this with the subsurface, so piezometric level and shearing zones that you may get from TDR or from shape array. And also to plot on the same cross section also structural data. So if you have faults or high persistence joints, to plot them, as well as stratigraphic let's say, changes that you may have between different formations. This is, in my opinion, very useful to interpret what's going on when it comes to understand the mechanism, okay? Another type of good way to compare, for example, piezometric data with surface displacement measurement is to plot, to use, let's say, point-wise piezometric data in a GIS environment or in a platform, and to show with colors as an heat map areas where there are the highest differences in pore pressure in a certain period. So you will end up with a heat map for several points that you can interpolate using any IDW or whatever interpolation algorithms, and you can compare, for example, with INSAR, or you can compare, for example, with the radar data, just trying to see if there is a correlation between the area with the maximum change in the pore pressure with the area where you have the maximum movements. This is something that in some cases was really worth doing, because it helped us to understand what was going on the below the surface.
Really good points. I'm glad you mentioned structural data in there too, in hydrologic data, because it all works together.
Jill, one little simple comment there. Sometimes it is easy to mess up georeferencing of the instrumentation. So make sure that all your instrumentation is very well georeferenced at the point that you are looking at on independent devices that may be just local points, local measurements of any parameter. Make sure that they are properly georeferenced, but also properly timed. I've seen interactions between surface and underground, very much related to blasting in either underground or in surface. And down to the seconds, it is important to have the instrumentation very well aligned in time so that you can make sensible analysis of the data. Simple concept, of course, everything has to be properly timed and georeferenced, but it tends to fail. So that aligning those things help a lot with an easier analysis later on. And also leave notes of when the blastings happen, when the blasts happen in your geotechnical instrumentation data, so that you can correlate later on. We don't typically record those things in our instruments, so you need to figure out how to also have a plot to compare against the behavior of other variables.
Yeah, very good.
That's a good point over there, Albert, for sure. And two, if people might not think about it as often, but that can be also another automated component too with the blasting. So other times people maybe think they have to enter that data automatically by hand into the data sets themselves, but there's also a database that can be tapped into to integrate that data in more of an automated fashion when a neuroblast occurred. So it definitely can be an automated component there as well.
All right, thank you for that. Chad, did you have anything you'd like to add to this based on your experiences?
I mean, the comments from Paulo were almost exactly what I was going to say. Bring it into some type of integration platform in 3D, bring in all the geology faults. If you have joint sets that are pervasive, try to represent them somehow with like either a form interpolant or a large disk that represents the set. Build conceptual models of the mechanism compared to the vector and compared to the radar data. So we make a lot of cross sections through different instabilities, trying our best to make sense of them. And we don't always make sense of them, but we're, it gets us a little bit closer.
Great, thanks. All right, so we were speaking a bit about conceptual models. We have a question that came in about numerical models and the integration of radar data with numerical modeling software packages. So first, I'll just ask for a quick response from each of our three major radar vendors that are present today on the integration capabilities that their radars have with numerical modeling software packages, so that data that can be exported and imported into numerical modeling packages. So let's just first touch on that. So I'll ask Priyanka or Sharla from Roytech just to comment on on that from the Reutech perspective? Maybe I'll skip it.
Sorry.
Oh, go ahead.
I-
Go ahead, Charlotte.
I was talking to myself. Yes, we definitely do have integration capabilities in that we can export a point cloud or even a DTM of the synthetic map, depending on what you want to look at, be it relative range, which is interchangeably called displacement or deformation, average velocity, velocity delta, and then into the more signal-based information such as coherence and amplitude and so on, if you really want to pull those things in for whatever kind of assessment. But normally it's the movement data that is actually utilized for design, performance assessment and calibration. Also backwards and forwards modeling of different instability modes, classes, movement patterns, and so on. And then also understanding the associated factor of safety or probability of failure of certain instabilities. And not just instabilities, it's also looking at the behavior of the pit slope as a whole. And as I touched on, that design verification component, which is very, very important. So I'll hand, I think, over to Albert or Cliff. But I think basically between the three of us as service providers, with rock science specifically, we kind of have the same data output that is then brought into their code.
Cliff or Albert? Whoever's faster with the unmute. There we go, Albert.
Well, I think that the best we can do is right now is provide the geotech community with the exported data. So there are ways to get that technically and commercially done. That's pretty much it.
And Cliff?
Yeah, I think that, you know, there's the different modeling software packages that are out there. Some of them are working with some of the radar vendors to try and find ways that formats that can be brought in easily. I know, you know, at IDS we've worked with Rock Science on that side of things, and I think that it's, you know, that will improve over time. All the connections of these things, it's kind of still in its early stages of understanding, and so I guess it's up to kind of the market to push in that direction as well, like what the value is there for the end users and stuff like that, between the companies that do modeling and the radar vendors themselves.
Gotcha.
I think also maybe just to add on that, I think as service providers from the radar side, we are also looking at future collaboration with people and asking users to let us know what it is that they require as well, so that we can build towards that more integrated numerical model integration. And I think also just going towards GIS type exports from the radar data so that they can be imported into other third-party softwares as well. Thanks.
I'd like to just add here is just the opposite end of that too, getting that numerical modeling results back in comparison to the radar data as well. I think is an important concept there to see how well responses are between the different data types that are being collected around the facilities, whether it be from the radar, or INSAR, ground-based radars, or even the point sensors themselves as well.
And then Paolo, Chad, Derek, any comments on either that first, I'm sorry, not that first question, but the next two questions on the value that's brought from bringing these integrations into numerical modeling software? Any thoughts on utilizing the models and the cyclical maybe updates that have to happen, and then just the goal of the overall process of what do you get out of it? Is it worth it? That kind of thing. Paolo, I saw you unmuted.
Yeah, I'm aligning with what the three previous speakers just said, but I think trying to address this specific question, no? We know that what are now the capabilities of this radar software to integrate the outcome of modeling and vice versa. What could be the value that we bring from this integration? From my point of view, first of all, it's a calibration of the outcome of modeling, because traditionally modeling people and monitoring people were working in silos. I mean, completely different background and completely different expectation. But in the end, we are looking at the same kind of phenomenon, and we have to find a way to put together, no? Because if the modeling is not matching with what we see at the surface, of course, there is a problem. The modeling is based on the wrong assumption. So it's important that we take advantage of this integration. And I have seen sites where this integration is working very well, because let's say modern modeling people are understanding that back analysis and calibration with monitoring data are essential to get reliable modeling and to understand the mechanism and to define the best mitigation strategy. I have seen some sites where, for example, modeling, the outcome of modeling have been used to identify overall instabilities. And once these overall instabilities have been identified from the modeling, all the efforts have been focused on trying to analyze and explore the monitoring data in order to check whether there was any indication, any confirmation of what the modeling was telling us, no? So, for example, using INSAR, because the movement were still in the early days, using subsampling radar. And this is, in my opinion, a good point, because you can be guided by the outcome you have from modeling, which you can do in the early days, no, of mining for all the phases of mining, but then you need to put the outcome on the ground. And monitoring is essentially capable of doing this. Not only radar, not only INSAR, there is, as always, the need to combine surface, subsurface, and hydrologic information and structural information.
Very good summary, as always, Paolo. Chad, did you have something to add?
Yeah, maybe just one little thing to add. So like Paolo was saying, we're using these for basically calibrations. If we see something in the field, we try to replicate it. And all these radars are line of sight. And so we can get the data in there very easily. Every single platform has some type of CSV export, and then we can just bring it into like FLAC 3D or RS3. And so, but the limitation with that is what you're comparing is, usually a total displacement or horizontal displacement compared to a line of sight image from a radar. So this year, when we're working in FLAC, we just gave one of the consultants we're working with just the radar locations and asked them to calculate the displacements in FLAC in the line of sight of the radar itself. So when we brought in the radar data and we displayed the FLAC displacements, that they're actually apples for apples, or apples to apples. And so anyway, that's just something we did kind of on top of that integration to make the modeling data look, or at least present the data in the same way that the radar would see it. And that's kind of helped in some of our calibrations for numerical models. So anyway, just like a little code that was written to produce a line of sight displacement. And we look at all the displacements, but just when we're comparing back to the radar, we'll switch it over to the radar view in the FLAC model. So, and Vajan from Equilibrium, he's actually sitting behind me today, developed that really quickly, I think like within less than a few hours. So.
Yeah, and aligning to what Chad is saying, I think, remember that the main outcome of modeling, numerical modeling, is deformation.
It's so simple, the maths, but
sorry, and the deformation can be compared with the strain that we can measure from monitoring, no? Could be from INSAR, but also from line of sight strain. So that's exactly the way to make comparable, because if you compare factor of safety with the displacement, it's not exactly the same, because factor of safety does imply the use of a failure criteria. Okay, so this is increasing the level of uncertainty. While if you compare deformation with deformation, that's something that could make very compatible, no? The two outcome. And as Chad said, you can also, from the 3D the formation you get from modeling, you can easily reproject along the line of sight you get from INSAR or from radar. So that's exactly, I mean, the way, in my opinion, the trend at the moment for integration of monitoring with modeling.
I think just to add to that, Paula, and Chad, that's such a lovely description of everything. I know that we're service providers between the three of us. Within our software, we've got built-in options to calculate specifically the line of sight. And for example, I've been involved in an instability that occurred a few weeks ago, and we were able to calculate very easily what the vector of movement was compared to where the system was actually sitting, and calculate the vector loss of movement, which interestingly actually did really affect the collection of data for that instability, because about 30% of the movement component was lost based on the vector of movement of the failure. So very important to take that into consideration. As we all know, and have these kind of calculations, which are relatively straightforward, actually, included in various software codes and such.
All right, thank you all. So we are nearing the hour here. I just wanted to, I've been reviewing some of the questions that have been coming in, and I just wanted to note that we're getting a number of questions on INSAR specifically. We did run a webinar on INSAR for mining applications last month, and the recording is available on our YouTube channel. Also, if you are a student in the radar monitoring course, you can enter those questions in the discussion board, and I can direct them towards the INSAR experts that sat on that panel that are presenters in the course. So I'd invite you to do that. I'm going to bring up a nice question that was submitted here by our live audience today that's perfect for ending a webinar. Looking forward to the future of integration data, integrating data at your sites. I'll ask just the panel to comment on this. What are the key points to consider in the future for integrating data from, it says both sensors, but I'll say all sensors. What is currently being worked on regarding radar data integration? So if the panel could just comment on where do we see ourselves now, where do we see ourselves going, and anything interesting you know that's sort of on the horizon for geotechnical radar data integration. And I will invite you to unmute if you would like to go first.
I think the main challenge of integration of ground-based radar data from different radars, along with maybe INSAR data as well, with vast areas of coverage, lots of pixels, not that much time frequency, but large area to cover. Another instrumentation of high density, like scanners or accelerometers, for example, that produce a lot of information. That is the main challenge: how to handle all of that amount of data, and how to look through the data and search through it and get answers quickly. So I believe that the key challenge so far is that all these technologies have been developed and evolved and optimized to work alone by themselves. But when you try to integrate all of that with other instruments, the data management is the biggest problem. So I think that we in the geotechnical community need to look towards what people like the Google Earth people do. They have different bigger databases than we do, of course, for sure. But the way they go through those databases is geospatial databases, and I don't know what other sort of techie words to describe what they do, but it's definitely not what we do. So I think that it requires a complete change in the architecture of the way we store data and search through it, which is a big architectural change. I think that is the most challenging situation at the moment.
And Will, I see you unmuted.
Yes, I just
Okay.
touched on Albert's comment there, as well as I think Cliff maybe mentioned earlier, but I think one of the aspects is getting that data together more efficiently as well, currently being worked on, and as well as in the future as well with the different data types, just more synchronous communication between different systems, whether it be the different radar vendors to the INSAR providers to the numerical modeling platforms as well. There's definitely improvements that can be made and are being made right now with the way the data talks to each other and get that more frequent as well. Kind of that cyclical pattern, like kind of moving in progress there.
I just wanted to add to that, Albert and Will, that those were also such lovely comments. One of the things that happened at Slope Stability, which was just a few weeks ago, is a kind of call to various service providers to be able to provide information in a similar format whereby we can start looking at data from different sources and different companies in a similar fashion so that we can go forward with looking at integration. I think what I've really enjoyed about this discussion is that the community is becoming more familiar with certain terminology. And I think my departing comments are going to be always remember your movement convention in the sense of is it positive or negative, because different service providers illustrate the data in a different convention. So when you are integrating data from centers, you might have negative, which means it's moving towards you from Reutech, but a prism is moving on a graph away from you, even though it's actually moving in the same direction of movement. So it's how it's illustrated. And then the other thing is, obviously, we've touched on the spatial and the temporal resolution. And the temporal resolution is especially important because the faster you scan, which we're all working towards, the more likely you are to actually capture that entire movement profile. So that's something to just consider. And as we touched on earlier as well, it's looking at very similar movement types and patterns, but there could be different magnitudes of that movement, even though the pattern is similar. So just a few things to think about when looking at integration from a variety of sensors.
Yeah, and I think that's really good comments from everybody. I just wanted to, definitely highlight what Albert said before, which is the data management aspect, especially I think it's we're getting really good, everybody, at making lots of data at the mine site, having tons of sensors, piezo's, radars. And we all have, mostly independent systems that can bring that in and process it and show it in nice ways. But I don't think there's a platform that brings it all in and shows it all really nicely and then also manages the data well. So it might just bring in some CSV 4D and you do some nice analysis and you have some decisions to be made. But then 2 years down the road, you don't have that, that CSV doesn't really have a record of much information other than what you exported. So I see kind of a problem that needs to be solved, which is just the data management of a history of, okay, here's the types of movements we've had historically through our mine, and how do we filter through those and see all the data sets behind those and categorize them so we know, oh, this was this, issue or movements that we're having 3 years ago in the same area. Here's the piezo data, here's the radar data, that doesn't really exist for most geotechs now. They just kind of can only go from real time forward or maybe a little bit back with some of these systems, and things get updated and changed. And so I think maybe a really important thing for the industry that would be so nice for the mining companies and geotechs is to have a really good data management and record of how their wall performance is and what the data is on all the different walls are and stuff like that in the future. Yeah.
We have a new team within Rio Tinto that's focusing on kind of upping Rio Tinto's game on how we manage data. So we actually have an hour-long meeting today where we're gonna develop a map of all the different geotechnical data and hydro data, and where it all sits. And we've tried to integrate it, but it's not all integrated completely. And hopefully we'll launch a project to better integrate it in the future. So anyway, it's still a challenge, even though we're using just the best stuff on the market. And yeah, it's still a challenge.
I think
Chad, I
that
just want. Oh, sorry, Albert, you go on.
very quickly, Charlotte. I think that currently perhaps I may be wrong, but I believe that perhaps the trend is to have the data integration as a dashboard where you can have some key parameters from different devices, not all the in-depth amount of information that every device could give you, but a dashboard that would let you be aware of something that is going strange so that you can go to the specific vendor software to do the in-depth analysis for real-time monitoring. I don't think right now the integration is happening for safety critical monitoring. And I said that from the point of view of ground-based radars, which is very safety critical. And people still tend to ask or request for the alarms and safety management to be handled by the vendor software because there are less points of breaking of the communication and the flow of information. Just because of that point, there are so many uncertainties when we develop the software in-house. There are already certain possibilities of breaking the communication, which is not conducive to safety critical monitoring easily. Could be done, but not easily. So dashboard style is what currently I believe is the trend. And definitely lacking all the historical good in-depth analysis with all the variables and all the events as Will was alluding to a couple of minutes ago. Sorry, Charlie, it went longer than I wanted. Sorry.
No, I always enjoy listening to you, Albert. I always learn a thing or two, so no worries. I completely agree with what you said. And, you know, kind of what comes to my mind when you talk about that is I do agree that a lot of integration is taking place, but it's from a much bigger picture. It's not from specifically a safety critical perspective. So we have to, you know, obviously be very careful with that. From a practical consideration component, as you mentioned, there are a number of things that can go wrong in safety critical monitoring, and those need to be included in the trigger action response plans. We're not just talking about alarms and reactions to movement or deformation accumulation. I know we've basically almost finished here, but also just consider the more mechanical components, but also understanding the signal quality is something to think about. And yeah, I just think we just have to be very aware of what precisely we are looking at and how we're applying it. Those were just a few comments that I had. Thank you.
Thank you, Charla, and thank you to all the rest of our panel, some of which had to drop off at 9, but we really appreciate you all being here today. We did run a few minutes over, but that's just because we were having such great conversations. If you're a participant in this webinar and your question did not get addressed, I'll welcome you to either post your question on the discussion board on the radar monitoring course site, where I can connect you with the relevant presenter or panelist, or send an email to gce@arizona.edu so that we can make sure to get your question addressed by our willing experts, who we appreciate so much. Thanks for being here, everyone, and we'll see you at our next webinar. Date is to be determined, but the topic will be operational response to radar monitoring data. So keep an eye out for that on our LinkedIn, or if you're a course student, it'll be announced on the course site. So thank you so much, everyone. Have a wonderful day.
Thank you, everyone.
Thank you, everybody. Take care.